All right, everybody. So now we're going to start our lecture on chemical quantities in the mole. And what this is, it's really connecting ideas of chemical reactions and chemical formulas, right? Chemical reactions and formulas for individual molecules to dimensional analysis. And it's all for the purpose of calculating the amount of a substance needed or used / produced in a reaction, right? So we're going to be talking about now if we mix a certain amount of two things together and we know the chemical reaction, how much are we going to produce? Or if we have a certain amount of a given substance, what percentage of that is related to hydrogen, carbon, so on and so forth, right? So the first thing we need to do is build up the idea of the mole, right? So it's more convenient to use mass relationships while in the laboratory. And why is that? Because we can't actually count the number of atoms or molecules that are involved in a reaction, right? We can, however, weigh things before we put them into a chemical reaction. We can determine how much we have by weighing the the amount of each reactant. And so in order to relate the mass and the number of atoms, chemists use an abbreviated unit called the mole, right? And really all the mole is, a lot of students tend to struggle with this, but it's really just what we call a counting device, right? And what does that mean? It just means it gives us another way to count certain things. So for example, a counting device that you're all familiar with is if we think about a dozen, right? A dozen things, right? 1 dozen things is equal to 12 of whatever that thing is, right? That's equal to 12 of that item specifically. And so 2 dozen, right? If we were to convert that into the actual amount would be 24. 3 dozen, things, we convert that and that would be 36 things, right? So for each of these, it would be 26. That's the actual number amount. But the dozen represents the counting device. It represents a number of 12 of whatever that thing it is that we're talking about, right? And so the mole is a similar idea, except it represents a very large number of things, right? So it represents an Avogadro's number of things, right? And that's 6.022 times 10 to the 23, right? So Avogadro's number is abbreviated N sub A. And N sub A is equal to, with units, 0.22 times 10 to the 23 things per 1 mole. And this is exactly like what I had on the previous page, except in the previous page I had these are all conversion equalities, and this is more like a conversion factor, right? If I extend that, fraction sign right there, this would be a conversion factor, right? And so 6.0 times 10 to the 23 things is equal to 1 mole of those things, right? And I put things because you can use a mole to describe anything. It doesn't have to be atoms or molecules or ions. It can be stars, right? So for example, if I have 1 mole of galaxies in the universe, that means I have 6.0 times 10 to the 23 galaxies in the universe, right? And so the reason that we just say it's a counting device and the reason we need such a large counting device is because we're dealing with things that are very, very small, right? So if something is very, very small, right, when we're dealing with macroscopic amounts of them, so like a gram of atoms, right? 1 gram of atoms, right? That is a large amount of atoms, right? So whenever we have a gram, which is stuff that we actually would measure in the laboratory, that's about the size of things we'd measure. Whenever we would have a gram of them, we don't want to say that we have 6.0 times 10 to the 23, 6.022 times 10 to the 23 atoms involved in this reaction. So it's easier to say than, okay, we have 1 mole of that substance, right? It's the same way that if we said, okay, well, how many donuts do you want? Well, I want 2 dozen donuts. That's a simpler way of representing, well, I want 24 donuts, right? 24 donuts is a larger counting number, right? So it's easier to say that we want 2 dozen donuts. And so the mole is the exact same idea here, right? And so when we talk about a mole, if we say we have a mole of hydrogen atoms, that means that we have 6.022 times 10 to the 23 hydrogen atoms, right? Gives us a direct conversion between the amount, right, the physical counting number, and a molar amount is what we would say. If we say we have a mole of H2 molecules, then that means we have 6.022 times 10 to the 23 H2 molecules. If we have 1 mole of H2O molecules, then that means that we have 6.022 times 10 to the 23 water molecules. And if we have a mole of sodium ions, that means we have 6.022 times 10 to the 23 sodium ions, right? So we're using the mole because otherwise we'd be talking about, a 10 million to the 10 million to the 10 million amount of these atoms, right? And the mole is an easier way to count these large numbers of things, right? It also introduces a new unit to us, right? The SI unit is a mole, right? So 1 mole of things equals 6.0 times 10 to 2 times 10 to the 23 of those things, right? And now that gives us also conversions now between moles and numbers of things, right? So the mole is a conversion between number of things and the unit, right, which is our counting unit of the mole, right? So we get 1 mole equals 6.022 times 10 to the 23 things, and then the other way around is 6.022 times 10 to the 23 things per 1 mole. And again, things can be replaced by any unit, number of atoms, number of ions, number of molecules, and so on and so forth, right? So these are our conversion factors, right? We can use Avogadro's number as a conversion factor. And which one we use just depends on which way we're going in a specific type of conversion. Okay, so we have Avogadro's number basically goes between moles and numbers of things, right? So that's what this important takeaway is, right? The conversion between moles and the numbers of things, right? And so then that's not extremely useful as of yet because we don't just use numbers of things and moles in the lab. We actually weigh things out. And so how do we do that? Well, we use what we call the atomic mass or the molar mass of a substance to then convert between mass and moles. And usually we abbreviate it as MM, right? That's how I abbreviate the molar mass, right? And so what the molar mass represents is that the mass of 1 mole of that substance, right? So for example, if we look at hydrogen atoms, right, the atomic mass is 1.008 AMU, which is saying that the mass of 1 mole of hydrogen atoms is equal to 1.008 grams, right? So this is now looking at a conversion equality that goes between mass and moles, right? So the molar mass is a conversion between mass and moles, our counting unit, right? So now we have 2 conversions, the number of things to moles, which is Avogadro's number, and then the mass to moles, which is the molar mass, right? And where do we find the molar mass? Well, the molar mass is on our periodic table, right? Our periodic table. And on our periodic table, usually we have the atomic number here, our elemental symbol here. Then the molar mass is the number below, right? So this is the location on the periodic table, right? It's the number below the elemental symbol in these cases, right? And so for each element, we have a specific molar mass. So for hydrogen, it's 1.008 0.008 grams is equal to 1 mole of hydrogen atoms, right? The mass of 1 mole of hydrogen atoms. For chlorine, it's 35.45 grams for the mass of 1 mole of chlorine atoms. And chlorine is a bigger element, so you would expect it to weigh more, right? So the molar mass, right, we find from the periodic table, it's given in units of grams per mole, right? So that's one other thing we'll emphasize here, right? The units for the molar mass are grams of whatever that substance is per 1 mole of that substance, right? And you could get that from the conversion equality we have here, right? So this would, for hydrogen, for example, it would be 1 mole of hydrogen atoms per 1.008 grams of hydrogen atoms, and then the inverse of that as well, right? So the mole, right? The mole is just a way that we can count large numbers of things, and the molar mass gives us a conversion between mass and moles, right? And if you ever forget that, just think of the name molar mass. It has moles and mass in the name. Those are the two things that it's converting between. Okay, and so the molar mass of a substance is called, again, the atomic weight. Sometimes you'll see other people with the molecular weight, molar mass. These can all be used interchangeably, and we usually abbreviate it mm. So it's measured in units of grams, not just grams, but also grams per mole of that substance, right? And then we have the molecular weight, right? So this is 1 mole of substance. It's not necessarily atomic, right? If we have a molecule, then we have to add up the molar mass of each of the components, right? So the molar mass of oxygen, or of hydrogen, sorry, is equal to 1.008 grams per mole. And the molar mass, I'm using the subscript to indicate for atomic, right? So the element oxygen is 15.99 grams per mole of oxygen. This would be for mole of hydrogen. And if we wanted to calculate the molar mass of 1 mole of water, which is a substance, right, a compound, right, we just need to add up the total molar mass of all the atoms that are involved in the molecule, right? So the molar mass of water is going to equal, we have the molar mass of hydrogen that's going to be involved. However, there are 2 hydrogen atoms, so we have 2 times the molar mass of hydrogen plus the molar mass of oxygen, because we only have 1 oxygen atom, right? So this subscript comes into play as we multiply that molar mass by the subscript in the molecule. And so we can plug all this in. We get 2 times 1.008 grams per mole plus 15.99 grams per mole. And you plug that in, you calculate it, and you get that this is going to be about 18.02 grams of H2O per 1 mole of H2O, right? So the molar mass of any molecule is given as the sum of the molar mass of all the atoms within that molecule, right? And again, the molar mass, right, this is a conversion between mass and moles. And so why does this even matter? Why do we use moles instead of just using the mass? Well, it's because molecules, right, the atoms contribute different masses to the overall molecule. And in chemical reactions and chemical equations, you can think of the same thing. Each molecule doesn't add up to the total, the total mass is the same on both sides of a chemical reaction, but the atoms that are breaking and forming bonds don't contribute equally to the mass of each individual molecule, right? Because, you know, if you add 1 carbon atom versus 1 hydrogen atom, right, the number of atoms exchanged is the same, but the mass is about 12 times different in what you've added or subtracted from a molecule, right? So we need to use the moles to be able to get accurate counting information when we convert between, the amounts of different atoms within a substance or products and reactants in a chemical reaction. Okay, so now let's do an example. Let's calculate the mass of 1 mole, right? And whenever you see the mass of 1 mole, this is the same thing as saying calculate the molar mass of CaOH2, which we know is calcium hydroxide, right? And so what we need to do is we need to count up all the atoms. We have one calcium atom, we have two oxygen atoms, and then we have two hydrogens because the subscript is applied to both of these atoms, right? Because they're in parentheses out there. And so that means that the molar mass of this entire molecule is going to equal to 2 times the molar mass, or sorry, I'll do it in order that I put it up here. The molar mass of calcium, plus 2 times the molar mass of oxygen plus 2 times the molar mass of hydrogen. And each of these values that I've written here, I get from the periodic table. And so calcium's molar mass, if we look at the periodic table, is 40.79 grams per mole. Make sure we include our units, plus 2 times 16.00 grams per mole, which is just a rounded version of the one we used on the previous slide. It just depends on the periodic table you use, which value you use. 2 times 1.008 grams per mole, right? So I plug all this into my calculator and I get a total of 74.09 grams of calcium hydroxide per 1 mole of calcium hydroxide. All right, so this is how I'd calculate the molar mass of this entire compound. Okay, so let's go through another example. Let's see, how would we calculate the molar mass of lithium carbonate here? So the molar mass of lithium carbonate, or bicarbonate, lithium bicarbonate, right? Lithium carbonate is going to be molar mass of Li2CO3 is going to, we have 2 lithium atoms, so it's going to be 2 times the molar mass of lithium, plus we have 1 carbon atom, right? There's no parentheses down here, so this 3 only belongs to the oxygen. So the molar mass of carbon, plus we have 3 oxygen atoms, so 3 times the molar mass of oxygen. And so we look up those values in a periodic table. It gives us 2 times 6.94 grams per mole, plus the mass of molar mass of carbon, which is 12.01 grams per mole, plus 3 times the molar mass, which is going to be 16.00 grams per mole for oxygen. And we plug that all in, and we get about 73.89 grams of lithium carbonate per 1 mole lithium carbonate. And the reason I include the units here at the end when I finally calculate the molar mass of everything is because when we're doing these conversions, sometimes we're going between different elements and different compounds, and the moles that we're referencing of which compound has to be able to cancel out in these cases, right? So we need to specifically be talking about the molar mass that we need to use for these types of problems, right? So that's how we calculate the molar mass. So calculating the molar mass is something that's going to be extremely important to be able to do kind of just off the back of your hand, because this will be involved in every other step of every other type of question that we are going to be encountering, right? And so next lecture, what we're going to talk about is actually using Avogadro's number, the mole, and the molar mass to do unit conversions and to calculate chemical quantities from that. Okay.